Good morning everyone and welcome to today's webinar. My name is Keira Proctor and I'm the Managing Director of the Proctor Group Limited. And today we're going to look at pitched roofing and particularly the effect of air permeability throughout the roof structure. As usual, we'll follow up with a Q&A session, so any questions you have for our team you can type them into the chat box here, DM us at Proctor Group or email webinar@proctorgroup.com. When we think about roof design, the first thing that comes to mind is water tightness, keeping out the wind and rain to ensure the building stays dry. The full picture of roof performance is a bit more complex than that, however. Roofs don't just need to address external moisture sources, but play a critical role in managing internal moisture as well. Our approach to this at Proctor's is based around the management of heat, air and moisture across a building envelope, so let's begin with a brief recap of how these factors affect the design of roofs in particular. The heat within the building is the driving force of these interactions. The warmer a mass of air is, the more moisture vapour it can carry, and when the temperature is reduced beyond a certain point, this vapour will condense back into liquid. A simple example of this is moisture on the outside of a cold drinks can or a bathroom mirror. The occupancy of the building, everything from cooking and washing to simply breathing, increases the moisture load in the heated spaces, and as the temperature varies throughout the roof, the capacity of the air to retain and transport this moisture varies. So, the design challenge with roofs is to ensure the moisture from the building occupants can safely pass out through the fabric without condensing into liquid water. This condensation can cause a range of problems in building, from swelling and distorting timbers to mould growth and decay, so it's very important to ensure the moisture content in a roof is properly controlled. The moisture is transferred from the living space in two principal ways: diffusion and convection. Diffusion occurs when the heat-driven vapour pressure internally pushes the vapour through the pores of the materials themselves. Different materials permit this to varying extents, with plastics and foils providing an effective barrier, whilst fibrous loft insulation allows easy passage. Convection, on the other hand, is the flow of moisture-laden air through gaps and cracks in the element, such as around a poorly fitting loft hatch or through unsealed downlighters in a ceiling. This unplanned air movement can increase condensation risks in two ways. Firstly, by transporting warm, moisture-laden air into cold areas, such as bypassing a poorly fitting insulation board, which may have otherwise been reasonably vapour-tight. And secondly, by allowing colder air from outside to infiltrate into warmer areas, potentially creating cold spots. In both these scenarios, the likelihood of warm, moisture-laden air contacting cold surfaces becomes higher than anticipated, leading to potential condensation risks and associated moisture problems. This transfer by convection is also typically more localised than diffusion, so can lead to very high moisture contents in specific areas, which may be harder to identify and remedy than a more widespread issue. Ensuring the transfer of air and moisture into the roof is minimised is therefore an important first step in ensuring a successful design. There are two main codes of practice that cover this: BS 5250, the wide-ranging code of practice for the control of moisture that we've discussed before in our series of webinars, and the similarly named BS 9250, which focuses on the ceiling itself. The recommendations given in BS 5250 are referenced in the building regulations across the UK and Ireland. We'll talk about diffusion of moisture shortly, but let's begin with looking at how we can create an effective barrier to the movement of air. To achieve this, BS 9250 gives the following criteria for a well-sealed ceiling, which is judged to sufficiently limit convection. These criteria are: avoiding gaps in the construction and holes through the ceiling, especially at wall-ceiling junctions; no roof access hatches in rooms where large amounts of moisture are produced, such as all bathrooms and kitchens; a limit of 1 cubic metre per hour at 2 pascals of airflow through loft hatches; all penetrations such as surfaces and roof lights are permanently sealed. The ceiling is sealed to the external walls to limit airflow through cracks. Total air leakage through all recessed light fittings not more than 0.06 cubic metres per hour at 2 pascals of pressure difference across the ceiling. Any wall cavities should be sealed at the head to prevent moist air entering the loft. As well as this, it makes recommendations for how the air barrier layer, whether a dedicated membrane or sealed rigid sheets such as plasterboard or plywood, can be detailed. It's here that some important points are made. When using rigid sheets as an air barrier, joints should always occur over a solid base, such as a joist or purlin, as these boards require the edges to be fixed. This makes them straightforward to seal as the joints are well supported and fixings will be sealed but the final coat of plaster finished. Where an AVCL membrane is used, its performance in restricting both air leakage and vapour movement by diffusion will only be as good as the quality of the seals at the joints and penetrations. This means it's critical that seals are both effective and consistent. If a joint is made over a compressible substrate like a mineral fibre, it can be very difficult to exert sufficient pressure to seal the joint properly along the full length of the lab. This can allow gaps to open, which will allow the passage of air and vapour. If the joint is made in a joist line, however, the tape can be fully compressed, ensuring good adhesion and reducing the potential for these gaps. Similarly, it's important that fixings are sealed. If the membrane is simply stapled to the timber, this punches holes which can allow air and vapour to pass through. If the membrane is not sufficiently durable and reinforced, these can open into larger tears, which may not be apparent until problems arrive after the sealing is completed. Another example where detailing is important comes where an AVCL membrane is omitted. In some cases, when using our Proctor air underlay, the additional diffusion resistance provided by an AVCL may not be needed. In such cases, it's important to ensure the sealing edges are convection tight against the wall. It's not simply a case of lapping the sealing AVCL onto its counterpart within the wall. Here, we can see an example of this type of junction where a bead of airtight sealant is used at the edge of the sealing boards, along with a strip of plasterboard jointing tape. The wall board is also fixed with a continuous horizontal ribbon of bonding adhesive at the top of the board, and an air impermeable cavity closer is present at the top of the wall. So we now have our sealing well sealed. We can look at diffusion resistance. This involves the properties of the materials themselves and the vapour pressure created by the temperature and moisture in the living spaces. Here we can use the methods given in the BS EN 13788 standard to calculate the condensation risk in the roof construction. The thermal and vapour resistances of each layer gives us both the expected temperature and the point at which the air will reach what's called its dew point and release moisture back into liquid condensation. If this dew point occurs in an undesirable location, we can seek to resolve this by varying the vapour resistance of the internal and external layers. Internally, greater resistance will limit the ingress of moisture before it can cause a problem, while externally, lower resistance will remove the moisture more quickly, again reducing the likelihood of condensation problems. Strategies for managing this are the principal focus of BS 5250, which we'll discuss now. The strategies outlined to deal with moisture in roofs depend first of all on the type and configuration of the roof, and BS 5250-2021 defines 4 basic pitched roof types, with the pitched roof being over 10 degrees of pitch but less than 70 degrees. Cold pitched roofs. In this type of roof, the insulation is placed horizontally across the ceiling ties, with the loft space and the structure of the roof being out with the building's heated envelope, hence cold. This large loft void can allow large amounts of moisture-laden air to accumulate in the roof structure, so to ensure this is managed correctly is very important. This type of roof typically uses fibrous quilt insulation, which is both air and vapour permeable. Warm pitched roofs. In this roof type, the insulation follows the pitch of the roof, either between the structural members, over the top of the structure, or a combination of both. This leaves the enclosed space under the pitch as part of the heated envelope. In warm pitched roofs, it's more common to see the use of rigid foam insulation, which tends to be more vapour and airtight than fibre insulation. This is primarily due to the thickness of insulation required to meet thermal standards, however, and there's no fundamental reason permeable insulation types cannot be used. Because there's relatively little unheated void space in this type of roof, condensation risks are typically a little lower than for cold roofs. Hybrid pitched roof. This type of roof, also known as a room in the roof, has a mix of horizontal, vertical and inclined insulation. This means some parts are cold roofs and some are warm, with a corresponding mixture of insulation types commonly used. The various junctions between the horizontal, vertical and inclined sections found in this kind of roof also pose additional challenges when it comes to detailing and specification. Structural insulated panel roof. SIP roofs use panels which combine the supporting structure and insulation layers into a single panel. Typically, these panels are comprised of a rigid foam insulation and timber sheeting like OSB or plywood. All these component parts are relatively air and vapour tight. BS 5250 gives guidance on how to control moisture movement by means of providing ventilation to the roof space. Let's look at a cold roof in more detail to see how this works. In a cold roof, there's a large void, the loft, where moisture-laden air can accumulate. This moisture may arrive in the loft by either convection or diffusion, but either way it needs to be removed. If this moisture contacts the cold outer surfaces of the roof, it can cause condensation. The solution of BS5250 is to introduce airflow to the loft, with ventilation openings at the eaves of the roof and sometimes also at the ridge. This allows air to pass from outside into and out of the loft, removing the moisture and reducing the risk of condensation. This has been used for many years as the main way of controlling condensation, and if it works as designed, there's nothing wrong with this solution. Where problems can arise is if anything blocks or constructs this ventilation, such as items stored in the loft or homeowners sealing up the drafts in the roof. Complex roof shapes and layout can also cause issues if the airflow is not evenly distributed around the roof. Rooms in the roof can also cause this issue as the airflow must negotiate some complicated structural elements within the roof. In such cases, it might be necessary to introduce some additional tile vents to the roof, but these can look unsightly, complicate the specification and installation, and increase costs. In these circumstances, vapour permeable underlays can help by allowing the ventilation to simply be removed. Vapour permeable underlays, or type LR membranes as defined in BS5250, allow moisture vapour to pass through, driven by the internal vapour pressure. In theory, this means vapour can escape through the whole roof surface evenly, which means there's no complex air movement to account for. In warm roofs, this approach works well, and an airtight membrane such as our Wrap-Tight can help reduce the overall air leakage rate for the building and simplify details. In a cold roof, though, it's not quite as simple. In these areas, the large roof void allows for more moisture accumulation, and this is not always effectively transferred through an airtight membrane. This is especially true in the initial period after construction, where moisture from concrete, plaster and other wet trades needs to dry out. Airtight membranes therefore may require additional ventilation to cope with this moisture, such as the 5mm ridge opening required by the NHBC, or might need increased vapour resistance across the ceiling. Proctor Air, which is both vapour and air permeable, provides a solution to the problems inherent in both ventilated roofs and vapour permeable underlay. It allows vapour to escape by diffusion, but also allows air movement through the voids in the roof. This means the movement of moisture vapour out of the roof is much more comprehensive. In our room in the roof example, it also means the same membrane can be used across the whole roof regardless of the internal layout, whether room in the roof is present or not. As the whole roof is, in effect, one giant ventilation opening, the size and shape of the roof also has no effect on the requirements. An air and vapour permeable underlay will perform the same on a complex roof as on a simple one, with airflow evenly distributed around the whole roof. Because of this, it's possible to use Proctor Air without necessarily requiring the use of a vapour control layer at ceiling level, although vapour ingress by convection does still need to be controlled as we discussed earlier. Another important advantage of removing the ventilation from the roof is that it becomes easier to ensure the loft insulation extends fully into the eaves. This is significant because if this insulation does not extend far enough, it can cause a cold bridge at the junction within the wall, leading to localised cold spots and potentially surface condensation and mould growth. If ventilation is required at the eaves, a gap must be maintained over the insulation, typically using a plastic former to ensure this remains unobstructed. In practice, though, what can happen is that insulation is stopped short or not pushed in, leaving gaps at the point where the heat loss at the junction is highest. With modern building regulations requiring significantly thicker loft quilt than in the past, ensuring the insulation layer is as continuous as possible is critical. If ventilation is removed, a rigid eaves carrier can be used to ensure insulation can be packed into the eaves to the greatest thickness possible, minimising the effects of cold bridging at the junction. BS5250 does not directly address the removal of ventilation though, with both vapour permeable and air and vapour permeable membranes acknowledged in the Code of Practice but not discussed in detail. If this type of solution is proposed, the standard refers to a third-party certification, such as a BBA certificate, which will give more detailed information for a specific membrane specified. As well as air permeability or otherwise, there are many factors such as requiring batten spacing, fixings and joint taping, which can vary considerably between different underlay membranes. It's important to be aware of these requirements and to ensure the as-built roof matches the design specification, as not all LR-type membranes are interchangeable. So, we've seen how air permeability can be either a negative or a positive factor depending on the location within the roof of the air movement. Like many things in building design, this underscores the importance of a holistic and well-considered approach to the design of roofs, taking into account the full range of performance factor. With this in mind, the final part of the roof we need to consider is the outer covering itself and how air and vapour movement occurs in this area. When roofs are ventilated in accordance with BS 5250, it's generally assumed that no significant amounts of moisture will reach the outer covering due to the ventilation lower down. But if we make the underlay vapour or air and vapour permeable, then we must follow the movement of vapour into this area and assess its effect. While some outer coverings like profile metal sheets are mostly impermeable, and as such require ventilation between the underlay and the sheeting to remove moisture, most slate and tile assemblies are permeable to some extent and will allow the moisture from within the roof to pass through. BS 5250 requires the outer roof covering to have an air permeability of at least 17.4 cubic metres per hour at 10 pascals. When tested using the method given in the BS 5534 Code of Practice for slating and tiling. BS 5250 also notes that most common discontinuously laid coverings, such as concrete or clay tiles or natural slates, can be expected to exceed this. One situation not directly considered in these standards is the use of integrated photovoltaic panels in the roof construction. Historically, PV panels have typically been mounted externally to the roof, but with increasing use of panels, systems that build the panels into the slate or tile assembly directly have become more common. In these situations, the roof assembly is neither continuous panel nor a fully discontinuously laid covering. Is the air permeability and moisture movement through the adjacent tiles sufficient to offset the continuous area of the PV panels? To resolve this question, we look back to a project we were involved in many years ago. This project, the Partners in Innovation Study, Improved Thermal and Moisture Performance of Pitched Roofs, was coordinated by Glasgow Caledonian University and focused on testing and modelling the effect of air movement in and around pitched roofs. This project led to the development of the Advanced Roof Cond modelling software, which can simulate air movement and condensation risk in roofing, including in and around the tile assembly. Using this software, it's possible to model the conditions in the batten space under the integrated PV panels and adjacent tiles. The outcome of this revealed that even with the air permeability of the outer covering reduced by 80%, there is still sufficient air movement to remove moisture before it reaches problematic levels. To ensure sufficient air movement is maintained, we recommend the following installation guidelines when utilising Proctor air with photovoltaic panels. Firstly, the underlay must be draped between rafters as recommended in BS 5534 to ensure a gap between the underlay and the tile battens of not more than 15 mm. Proprietary PV mounting trays or counter battens may also be used provided a similar gap is maintained. Secondly, the tiles or slates used across the remainder of the roof must not be airtight when tested in accordance with the method in BS 5534 Annex L. This means that the pressure drop coefficient at 2 pascals of pressure should be less than 25,000. Lastly, there should be at least 2 courses of this air permeable slate or tile system above and below the PV panel, or a dry ridge system that provides equivalent air movement. There should also be 2 tiles or around 600 mils of tiling either side of the PV panel. The extensive study and modelling that led to these recommendations has also allowed the granting of Proctor's BBA certification for use with integrated PV panels, allowing its use on NHBC projects. This commitment to testing and certification, combined with years of experience in the design and specification of pitched roofing, is what sets the Proctor Group apart. We'll now move on to the Q&A session. Good morning, everyone. Welcome to our final webinar of 2025. Thank you very much for attending, and I hope you're all doing well and looking forward to Christmas. So this is our 5th webinar of 25. We've done slightly less this year than in previous years, but next year we will be doing more frequent ones, so certainly bi-monthly, if not monthly on occasion. So we're going to try and get a schedule worked up so that if you want to come to more regular webinars, then you can do that. We've almost 250,000 views to date of our webinars, and we hope to continue to grow that. So as some of you may know, we will try our best to answer all of your questions, so please feel free to ask them here on the YouTube feed. We've already got a lot coming in via email at webinar@proctorgroup.com, or you can DM us on social media channels at Proctor Group. If you'd like to request a product sample pack containing any materials discussed in this, or book a meeting with either our technical team or one of our technical sales reps, then you can do that on the webinar page. And that's where you'll also find your personalised CPD certification for today's webinar. If you've registered, you'll receive a follow-up email with all of these links and a link to the replay. So late registration is still available, so please feel free to do that to get a copy, and you can then circulate it to colleagues or anyone who may be interested. It really helps us if you give us a thumbs up if you enjoyed today's webinar, and if you subscribe to our channel, it keeps you informed of anything that we have coming up. As I say, a bit more of a full schedule next year. So this week we have some familiar faces and some new ones. So we have Pamela Howitt, our senior technical advisor.
Morning, Keira. Good morning, everyone.
Morning, Pam. We have our technical advisor, Sue Menmuir.
Hello.
A new face for the webinars, but someone who's been here a long time, Graham Berry, our technical marketer.
Morning, Keira. Thanks very much.
To be fair, Graham's normally behind the scenes, but he's very technically capable on the product side. So we've dragged him into this one. And last but not least, our special guest, Chris Sanders. Chris has over 30 years of expertise in building moisture, condensation, thermal insulation, and standards development, having worked with BRE for many years and other organisations. So led major research, authorised key industry guidance, and continued as a consultant following his academic career. Good morning, Chris.
Good morning, all. Here I am.
Morning, and thank you for joining us. Okay, so I'm just going to jump right in. As I say, if you have any questions, please make it clear that they're a question, and I will make sure that it's directed towards someone. So a ton coming in already, so I'm just going to jump right in. And to pick on somebody, I think we'll go with Sue. So Marina Phillips has asked, do you need a temporary cover when using Proctor Air? I think Sue's struggling to get unmuted. Let me jump to another one. That is not a problem.
Got it now.
Got it. Perfect. It's been a while since we've done it, Zoom, so
I
don't
know,
worry.
sorry. It's like struggling to know where to click.
No problems.
Temporary cover. Most pitch roof underlays are designed to be used as secondary protection underneath your slates and tiles. So we always recommend that a temporary waterproofing cover be used during the construction phase if we're getting the type of weather that we've been experiencing here over the last wee while. We believe it's good practice. This is what we recommend. BBA also, they have produced an information paper on the same subject, and it really should just be standard good practice.
Thank you very much. Pam, David Graham has asked, you mentioned the water vapour rates that your product can handle, but does that figure what does it actually represent? So does it deal with areas of high humidity directly above a shower, for example?
Yeah, it's a really good question. It probably does correlate to that. So like things like the SD value, and Chris might correct me on some of this at the end, but it's relating to the sort of the vapour movement through like a metre of air, or the equivalent metre of air. So it's very difficult to correlate it in terms of physical quantity of water. What we can see is that with Proctor Air being air and vapour permeable, it's got two mechanisms for the vapour to escape out of it. So it will allow vapour to move by diffusion through the material, but also on air through the air permeability aspect of it. I think we touched on, things like your ceiling should be well sealed in your areas of bathrooms and showers. They do need to be properly ventilated. You do need to look at things like recessed lightings in those areas are really not ideal, because they can provide localized areas of high humidity getting into the loft space. Now, that's not to say that individual spikes at certain times in a day or a week is going to provide a long-term issue, but perhaps if you've got four or five teenagers, doing sports, having 2 or 3 showers a day in and out, that could cause more of an issue than somebody that's older living by themselves. And actually, to be fair, this was picked up a lot in the PII research that was done, where they looked at different occupancies, different permeabilities. So it's really about using, as a good breathable vapour and air permeable product ideally, or providing sufficient ventilation to deal with that, but also not overloading it, because you're not, it's all about managing, as the BS 5250 states, managing the moisture in the building. Don't rely on one thing to do everything. Look at it on the whole.
Good, thank you, Pam. And it's good to know that some teenagers shower frequently. It wasn't something that my friends have been aware of with their teenage kids. So. Okay, I'll skip a few and I'll come back to them, but just so we can engage with Chris. Chris, Paul Architect has asked, can you just tell me more about the PII research?
All right. Well, the PII research was carried out in about 2000. Shortly after that, there had been a well-established position that you could eliminate condensation problems in lofts, cold lofts, by ventilating the loft. But then around the late 1990s, manufacturers came along, Tyvek initially, but then the excellent membrane produced in Scotland, a roof shield, which were vapor permeable. And there were strong suggestions that we could eliminate the need to ventilate lofts and put in one of these vapor-controlled membranes instead. And at that time, because of some dreadful sin in a previous life, I was chair of the BSI committee that dealt with BS 5250. And there was a lot of pressure that non-ventilated roofs with permeable membranes should be allowed in BS 5250. And there was a great deal of argument about this. And the PII project, which was funded by government, that had about 10, 12 members from industry who were all very active and involved. We measured and modeled this situation and showed that provided there was a well-sealed ceiling, as you discussed in the podcast, and a permeable membrane, it was not necessary to provide as much ventilation in the loft, which was incorporated in BS 5250. Since then, the vapor permeable membranes, the air permeable membranes have come along, which provide an additional effective source of ventilation. So I would think now the situation is clear that with an air permeable membrane and a vapor permeable one and a well-sealed ceiling, you don't really need to provide any extra ventilation for the loft.
Super. Well, this leads quite nicely onto a question I'm going to direct to Graham, please, from Pixie Parrot. Can you please reiterate why an air and vapor permeable breather membrane would be preferable to just a vapor permeable membrane?
Yeah, it's a good question. Basically, what happens when your membrane's air permeable as well is you have a degree of air pushing through the membrane. So as air flows and as there's convection from the heat in the building, you have an extra mechanism which actually pushes the moisture out. So with an airtight membrane, vapor can still pass through it, but it's only using the vapor pressure by itself. There's no actual physical movement of air. So that mass movement of air with an air permeable membrane basically turbocharges the amount of moisture that can be pushed through the membrane. Because there's air moving across the surface, it also makes it very difficult for condensation to actually form because there's never still air around the membrane surface. So yeah, that's simple as that, basically.
Makes sense, thank you. Right, let me jump back and tick some of these off that have been asked. So Steve Roofer, thanks for joining us. So I think this is all one question. So do you think that adding thermal insulation at ceiling level, Pam, can I come to you on this one, please, has starved the roof void of the escaping energy that used to provide a natural drying ability and making that loft colder than it used to be? So could this be why we're now seeing more moisture-related problems than in the past, and why modern membrane development has become so important? It's a great question.
It's an absolutely cracking question, Steve. Thanks very much. Yeah, to be fair, I think you're absolutely spot on with this. Without a doubt, the increased levels of insulation. So historically, you would get quite a bit of heat naturally rising into the loft space, drying the timbers out, driving the vapour out, making quite a positive vapour pressure in that roof space. By quite rightly sealing our ceilings, so we're actually becoming more energy efficient and preventing too much moisture going up there, by adding in insulation, we're actually making that loft space predominantly mimic the external temperatures. So if it's cold outside, it's going to be colder in that loft space. I think it's particularly important when you consider, upgrades. People think, oh, it's great, I've got an old loft, let's just roll out a whole load of insulation. You could have quite leaky aspects of that, like your, loft hatch, whether the wall heads are closed off, etc. So actually, you could be getting quite a lot of moisture in there, which is then going into a colder space, which might mean that you've got more of an issue during the winter. So it is being aware of that and being aware that you do need to then control the moisture. We're possibly living differently. So buildings are warmer, or we're wanting them warmer, which can obviously hold more vapour, which when that then passes into the loft space, it's taking more vapour. We're possibly looking at more man-made slates and tiles, which may not have the same permeability through them as sort of more traditional clay man-made type tiles or slates that we historically used to use. So yeah, without a doubt, I think that we have to be much more aware of where all these vapours are coming from. Buildings being built faster, especially traditional builds, a lot of wet trades, that can take anything up to 2 years or more to properly dry out, and you can't force it, otherwise you get cracking, etc. So you will again additionally get excess vapour. So it's very much looking at what is the long-term best solution. Don't think about what's a quick fix for the install. It's what is going to work for this roof throughout the lifetime of this roof.
Super. Thank you very much, Pam. One from Eric Parks, and don't worry, I will jump back to other ones. Sue, if I can come to you on this person, maybe others will have some additional comments. Is Proctor Air suitable for use on Scottish roof construction, something that we know quite a lot about, where timber sarking has been installed directly on the rafters or trusses? Are there any studies or research on this? Thank you.
Yeah, absolutely. As a Scottish company, we come across sarked roofs frequently. Not an issue to use Proctor Air on traditional softwood sarking. It has been used, we've used membranes over the last 25, 30 years on this type of construction. Really quite happily, where you have your slates slated directly through in the traditional manner. There are more limitations when you move to sort of like more modern sheet sarking, like plywood or OSB, in which case warm roofs are absolutely fine. There's not an issue there. But when you're doing cold roofs with your insulation down at ceiling level with these more vapour tight sarking, sheet sarking boards, then that's when you would need to introduce ventilation. But your traditional Scottish construction with your softwood sarking boards, warm roof, cold roof, room in the roof, not an issue with Proctor Air.
Okay, perfect. On that, we did a bit of research on this, Pam. I don't know if you want to maybe comment on some of the stuff we did here in Blairgowrie, actually.
Yeah, to be fair, I think Chris was involved under Glasgow Caledonian. So it was when we were first working with air and vapour permeable underlays and trying to get the acceptance of their use without vents, etc. Actually, believe it or not, doesn't even predate my time with Proctors. But we actually did a project where we were able to put monitoring points in a new extension to a Victorian nursing home, care home in the town, quite an exposed site on the top of a hill. They essentially built a second story on top of an existing extension to that building, which still had the residents in situ. And what Glasgow Caledonian did was they took monitoring of that throughout the various seasons at various points, like at ridge eaves, midpoint of rafters, on the back of the sarking, etc., and analysed it. I should say there was no vapour control in that roof, and they had open water tanks in that roof space as well. So really all the things we kind of sort of say is not ideal. But that roof showed that the inclusion or the use of vapour and air permeable underlay, like the Proctor Air, on sarking with slates directly on top of it was no different to a traditionally ventilated roof. So that allowed the inclusion into our BBA certification and our comfort, and now 25 plus years track record of it being used. And my mum actually ended up in that particular care home, and it was still lovely and dry and functioning 25 years later.
Good. Fantastic. Graham, I'm going to come to you with one on email, just so people that have emailed know we've not forgotten them, and then come back to Chris on a couple of questions from the feed. So Alex has asked, why are warm roofs not adopted more?
Yeah, that's something we think about quite a lot here when we're planning things in the office. If you look at things purely in terms of efficiency and energy efficiency and how you build the most efficient possible roof, a warm roof's has quite a lot of advantages around energy performance and reduced air leakage and all this kind of thing. But humans aren't particularly efficiency minded, and I know I, for one, would be completely lost if I didn't have a loft to keep all my junk in and Christmas decorations and stuff like that. So it's almost accepted in the UK as a cultural norm that houses have lofts. What's important with this is that as suppliers of materials and as designers of buildings, we produce a structure that's fit for purpose, whatever the purpose might be. And if the homeowners in the UK decide that a loft is an essential part of that purpose, then designing a system that accommodates that is the critical part. So air permeable membranes are particularly useful in that sense. So if you're having a loft, then you have an air permeable solution. If you're not using a loft, then maybe an airtight membrane, something like our airtight, provides a simpler and more efficient way of adopting that. So it's about making sure we provide everybody with the right tools to do whatever job it is they want to do. But yeah, certainly without my loft, my wife would not be happy because the house would be a complete mess.
The British tradition, is it? And I made the mistake of not having a loft, so yes, I regret it. I've got a very full garage, so I think it's quite a British tradition to have, and I miss it. I do miss it. Chris, Paul Architect had asked on the feed, was RoofCond able to look at the area of a roof where some parts are permeable tiles and some parts are PV panels?
Well, the way a RoofCond works is it doesn't look at local areas of the roof. It looks at the roof as a whole. And we would represent PV panels by reducing the air permeability of that area of the roof. So if the 30%, if the 30% of the roof is covered with PV, you reduce the air permeability of the tiles to 70%, and then see what effect that has, rather than looking at condensation in specific areas with and without PV.
Okay, thank you very much for explaining that, Chris. I haven't given one to you, Sue, for a little while. So let me see what we can do here. Carl Monaghan has asked, again via email, can you discuss air open tiles more?
Okay, so we did obviously touch on the air permeability of the tile assembly in the webinar there. As a general rule of thumb, most tiles and slates are deemed to be air permeable enough that you're getting adequate air movement, etc., through them. Not so that you don't need to provide that additional ventilation. Even natural slates, for example, are absolutely fine. Where you come to more tight fitting outer coverings, such as perhaps fibre cement or metal slates, then that is when you then have to introduce ventilation either in the batten cavity or in the roof space.
Okay, super. And I've missed one right at the start, Sue. Maybe you can help with this one as well. With the low resistance with the LRM, do you recommend actually sealing the roof void? For example, paying attention to the close of eaves or to avoid cold air infiltration from outside?
It would be, yes, what we would suggest, you would always close off the eaves just to prevent that warm air movement from coming up into the loft space through your cavity. So yes, we would definitely recommend closing off the eaves in that position there.
Super, thank you very much. Pam, Steve Goodall has asked, how do you ensure that the air permeability of the roof covering is maintained throughout the lifetime of the tiles and slates?
Yeah, another great question today. Very much dependent on sort of standard homeowner care. most slates and tiles are inherently relatively leaky in themselves. So there is standards and test methodologies that you can use to check the air permeability. Leaky is probably the wrong word because you don't want your slates or tiles to leak. But there will be gaps and paths for vapour and air to pass through them, as well as the fact that they're kind of lifted up. Obviously, lots of debris falling on top of your roof and lots of moss growing along the joints is not good from a whole host of aspects. So it's really making sure that debris like that is removed on a regular basis, sort of your general roof maintenance that you're going to carry out. But other than that, it's actually very unlikely to be any long-term issues. There still should be sufficient vapour movement through those tiles for the vapour to escape. But you've also got to remember you'll also have vapour hitting the underside of the tiles, and at certain times they are condensing and running down the membrane into the gutters, which is also acceptable as well.
That's fantastic. Graham, I'm going to come to you for another one. Someone said they weren't hearing you particularly well, so just in case, I'm hearing you okay, but I know you obviously, so I can interpret you. So, but we'll try to ask the next question. If people are still struggling, we'll leave you alone after that. So I've kind of got two here. One was via email and one's quite similar from Maurice Garnett. So the one from Jeff via email was, do the panels need an airspace for efficiency? And then Maurice's question on the feed was, one of the last slides suggested a minimum 2 courses of tiles below an integrated PV panel. We tend to show panels tray directly sat at eaves with no tiles below. Are 2 courses a British standard requirement or a Proctor requirement?
Okay, yeah. So is that any better? I've swapped to the laptop audio rather than using my headset. Is that clearer
That sounds
for everybody?
better. Yeah, and
Good.
you look better
Okay.
too, Graham.
Well, we'll see about that. So basically the requirement to have airflow around the panels is to do with the panel efficiency and reliability. So every system has a certain degree of operating temperature range that it has to work within. And if you go too far out with that, then you start to have issues with initially the efficiency of the panel and eventually the reliability of the panel. So the airflow is to ensure that the panel is kept cool and within that operating range, because even in Britain it can get pretty warm sometimes. So that's why we need the airflow. So to come back to the question about the tiles and things, to ensure we have the airflow, we've modeled and tested and looked at various solutions, which is the tiles surrounding the panels, to make sure that there's enough ratio of air permeable tile to less permeable panel to make sure there's sufficient airflow to keep within that comfort zone of temperature. So anything outside of that, for now, we would have to look at and revise. So for now, the BVA certificate covers a certain solution, but we have never been a company to sit and just sit with the way things are. So we're always looking at other solutions and how we can extend and expand our advice and guidance to accommodate all these situations, because there's such a range of PV panels and PV systems and PV mounting solutions that are out there. Something that's universally applicable, which is the solution we have just now, that applies to most situations fairly reliably, is the key just now. And going forward, we can look at how we can expand that and open up other options. So, but what I would say is, if anybody's trying to or considering doing anything out with those recommendations, have a chat with Pam and Sue and our technical team here. It's something we can absolutely take on, and we like that sort of thing. Anything outside of the ordinary.
Yeah, they know their stuff. Okay, I've got a couple here, and I'm going to come back to Sue before we go back to Chris again. Can we use, well, I'm going to ask 2 because they're kind of similar. So there was one from Gilles Chalom. Can we use counter battens as an alternative to draping between rafters? And Peter had also asked why is there a maximum drape of 15 millimeters? So could you kind of take those one and the same, Sue, and answer them both, please?
Yeah, of course. Absolutely, though, a counterbattens perfectly acceptable as an alternative to draping. When you drape the membrane, really what you're doing in effect is you're using the top of that rafter as your counterbatten. So fully filling the rafters, having the membrane, then a battens, an absolutely perfectly acceptable alternative. Maximum 15 mil, that comes from BS 5534. The drape of the membrane, you don't want too much of a drape of a membrane. It's getting the balance. If you don't have enough membrane, enough drape, then you might get ponding at the back of your tile batten. So you have to allow adequate drape to allow drainage down to the gutter. You don't want too much drape because then potentially wind uplift, for example, you don't want that membrane being able to hit the underside of your tiles.
Super. Thank you very much. 2 in 1. Chris, can I come back to you? We were asking, someone had said via email, Clara, has this only been proven on a computer?
RoofCond was validated by testing against the data we measured in 4 measured houses in various places of Britain. I think 1 in Scotland and 3 in various parts of England during then, and showed that the measured data we were getting from them was consistent with RoofCond. The main way it's been used is to assume, as I said at the beginning, if you've got a roof with a completely impermeable membrane, the old 1F felt that they used to have, you needed ventilation in the roof to reduce the risk of condensation. So taking that as a base case, you could say that if we reduce the amount of ventilation, how much do we have to increase the permeability of the underlay, or the air permeability of the underlay, to compensate to achieve the same result as having ventilation with a impermeable felt, which was an established working solution. So it's really based on those 2 forms of validation.
Super. And while you're unmiked, Chris, if I can also ask, Paul has asked, will the rafter length affect the movement under the PV panel?
To a very limited extent, provided, as you said in the presentation, if you've got 2 tiles, 2 rows of tiles above and below the PV, which are not covered by the PV, that should provide sufficient ventilation. Or if the PV is extending right up to the ridge, you would have to provide some form of ventilation through the ridge to allow it. But as I say, provided you leave spaces, uncovered tiles above and below the PV, the rafter length won't affect it.
Super. Coming to the last few questions now. So if you have any others, I'll just tick one off myself here. Ian Robinson, you've asked about CPD certificates. You can download that yourself on our website, www.proctorgroup.com/webinar. Or webinars, I think it's webinar, and you can download it yourself there. Any problems, just give us a message. So as I say, last couple by email and on the feed. So if you have any final questions, please post them now or DM us. One in from John Regis here by email, a cheeky one. What about other manufacturers' membranes? Sue, do you want to answer that one? So essentially, what are other manufacturers saying?
Well, obviously, we embarked on this work with Proctor Air in mind. So we have done all the research. Chris has done all the work using Proctor Air as the membrane. So we can't really comment on any other membranes. Obviously, it would be up to those manufacturers to confirm or otherwise. What is unique to us, though, is that we believe the first manufacturer to have PV panels actually included in the BBA certificate. So the BBA have taken, well, we've provided all the information, all the research to BBA, and they've obviously concurred that, that with Proctor Air, this is, a fit for purpose solution.
Super, thank you very much. And again, Sue, while you're on mic still, Lennon has also asked, is there a fire risk under PV?
Fire risk. Yeah, obviously with any electrical device, then there is the potential for a fire risk, but that generally tends to be, it's more likely to be maybe a faulty panel or, poor installation that, rather than the use of PV panels as a rule of thumb. The panels don't sit directly on the membrane. And with the air movement below, then obviously you're not encouraging overheating or anything like that. The air movement will improve the efficiency of the panel, but it doesn't affect the membrane. The membrane itself doesn't increase the fire risk.
Okay, good. Thank you very much, Sue. Okay, so I think I'll do the last YouTube one, then come on to the final couple by email. So, Graham, if I can come back to you, please. Jan William has asked, does the introduction of MVHR reduce the moisture buildup in warm and cold roof spaces?
Yeah, so in theory it shouldn't, because MVHR, which is mechanical ventilation with heat recovery, for those that don't know, what that should be doing is managing all the moisture within the living spaces and extracting moist air and importing fresh, drier air, theoretically. Where you have to watch with all ventilation systems and roof spaces, though, is if they're functioning, if there's some damage to the ductwork. So if there's ducts running through the loft or through parts of roof spaces or through cold areas that become damaged or seals break, in which case they can import moisture to where you don't want it. So a properly functioning, well-specified, engineered to the building MVHR system shouldn't make any difference at all, because the habitable spaces should be functioning within a known range of values. In fact, it should probably actually be better, because it'll be much more controlled internal environment than it would be otherwise. But if anything goes wrong, or if there's any damage or anything's not installed correctly, then that's something you need to be aware of, not just for moisture reasons, but because the MVHR won't be functioning effectively, it won't be working efficiently in that case.
Super, thank you, Graham. Okay, last two questions, so please post them now or you can email us afterwards. So maybe this is one to kind of put out to all of you. Maybe we can start with you, Pam. Ian Cameron has asked, how can we improve air permeability in retrofit situations?
It's going to sound a bit controversial, but sometimes you don't want to. So quite often what you're doing as part of a retrofit is you're wanting to improve the energy efficiency. So one of the best ways for air permeability is to have voids, things like chimneys, leaky windows. They're all forms of air permeability into your building, but actually as a retrofit and for internal thermal comfort and energy efficiency, they should be addressed and looked at and controlled. So it's probably more vapour permeability is important. In your roof, air permeability for your underlay and your outer slate or tile covering is important to ensure that your roof functions. But probably in your walls, air permeability may not be the best solution. Vapour permeable options like our Space Therm, for example, and we have a number of membranes that sit very comfortably within those parameters as well. We've got various webinars, etc. I think our last one we did was on Space Therm, which in retrofit, so it might be worth you dipping into. But really, it's about sort of focusing on what you're wanting to do and whether air permeability or vapour permeability is what the focus is. But certainly if you're re-roofing your property, then considering something like Proctor Air, which is air and vapour permeable, is a great solution, especially as you don't then need to provide ventilation. You don't need to interrupt potentially internal lining, so you may have cornicing that you don't want to start ripping down your ceiling and putting in vapour control layers, which may be more important with other less permeable solutions.
Yeah, we do an awful lot of work with historic buildings, don't we?
We
So
do.
churches and things that you really don't want to affect the look and feel of. But I couldn't agree with you more, Pam, when it comes to the kind of fabric of the building and the walls. I think it's proven that air leakage is one of the biggest biggest factors when it comes to energy efficiency.
Absolutely.
So I think you're spot on with your answer there. Okay, I have one final question via email, so let me just grab it up here. So I'll come back to you again, Pam, for this one. So Daniel Knight has asked, are there any scenarios in which Proctor Air still needs ventilation at eaves or ridge or anywhere else, such as vent tiles, etc.?
Okay, yeah, great question. We do get this quite a lot. Kind of really two scenarios. So the first scenario is if you're using a sheet sarking, so something like an OSB or a plywood sarking over the roof, that essentially under 5250 turns that roof into an HR, a high resistance situation. So you will have to revert if you've got insulation on the ceiling or a room in the roof. So essentially if you've got cold voids, you will need to revert to ridge and eaves ventilation in accordance with 5250. The other one where you need to consider putting ventilation in is depending on the outer covering. So if you've got a close-fitting fibre cement slate or man-made tile or something that doesn't have a lot of vapour movement like metal sheets and tiles, they generally will need to have ventilation to the batten cavity and will need a counter batten and batten. So a decent void, 50 mil void to ventilate. If you can't ventilate that void for whatever reason, then you do need to come in underneath the underlay. And that's really about that escaping vapour. Once it gets through the membrane, where can it go? And really it's with the outer covering supplier to have done that testing and determine the air permeability and the requirements for any ventilation through their outer assembly.
Yeah. Again, they would be quite specific. You don't see a
Yes.
lot of that in kind of the
You
the
don't.
general mass building, but it's
Yeah,
good that we've
yeah.
got good guidance in
And
terms of what
certainly
you
on
need to
the
do.
sheet OSB side, you know, if you are going with a sheet OSB for there's a number of valid reasons, consider turning your roof into your warm roof. You know, that's the way to get around it, because warm roofs with OSB or sheet sarking are covered by our warm roof BBA certificate. So just take the insulation up in line with the pitch.
Super. And if anyone has any more specific questions, as I say, you can contact these lovely individuals, apart from Chris, because he doesn't work for Proctor Group, and the other 3 individuals in our technical team. So can I just say thank you very much for attending. That's us come to the end of the questions. If I have missed any, I apologise. We do look through them. If we'll come back to you directly, or you can email us at webinar@proctorgroup.com with any further questions. So as I said earlier, if you'd like to request product samples or you have a project you want to talk about, you can do that on our webinar page, www.proctorgroup.com/webinar. And that's where you'll find your personalised CPD certification as well. So when you get a follow-up email which has a replay to this, because I'm sure everyone wants to watch it again over the weekend, but perhaps you want to circulate it to a colleague or something, there's also a short survey. Please do fill it out if you can, especially today's, because it's the last one of the year. So if you have any comments on this one, or if you've been on prior webinars, we are really interested in the feedback, constructive feedback that can help us do things better. So we don't take it personally, and we do want to hear about it so we can improve things. And any ideas for next year's, things you want to hear more about, please make a note of it there. As I say, if you give us a thumbs up if you enjoyed today, it does help us, and please subscribe to our channel. So I just want to say thank you very much to Chris for attending. We really appreciate your input, and thank you for making time to come along. That's been great. I think he's trying to say you're welcome.
Yes, it's been really interesting. I've enjoyed it.
Good. Thank you, Chris. And thanks very much to Pam, Sue and Graham as always. And thank you very much to the people that watch live, because we wouldn't do these live if people weren't watching live. We would just do the kind of education piece. So I love the fact that we're answering all these questions without preparation. The team are so knowledgeable, and also the quality of the questions that come through from the individuals that watch them is very much appreciated. So wish you all a very lovely Christmas and a happy new year, and we'll see you back in 2026 with a new suite of webinars, and look forward to you joining in. Thank you very much.